Recording. Yep, we are recording. And let's go ahead and so this is let me cheat here. Power generation by a steam turbine. And all right, so this is in the videos for you guys to watch. So I'm going to draw a steam turbine. Typically let's see. We draw a steam turbine that looks like this. And then you have your shaft where you have work coming out. And then you have an inlet or coming usually at the top here. You have steam that comes in and then you have an exit and steam comes out. We usually have that as 1 and 2. And then you have a flow rate, 1 and flow rate 2. However, because this is one inlet and one outlet, again, you might need to review this in your chapter 5. The last lecture that I talked in, we know that the flow rate is the flow rates are the inlet flow rate is equal to the inlet mass flow rate is equal to the outlet mass flow rate, right? So in this problem, they actually give that to be 0.02 kilograms per second. So what they do is they give us a bunch of conditions here of the inlet steam, and they give us a bunch of conditions on the outlet steam. And what they want us to do is to find, let's see, I have my book here. It says it says determine the work, okay. Determine the work done per unit mass of the steam flowing through the turbine and to calculate the mass flow rate of the steam. Okay, I made a mistake. I'm mixing the two problems. So the example before that, which I did for my other class, had that, but this one they don't give us the flow rate. We got to calculate the flow rate. So what do they give us? Okay, so let me write down what they give us. They give us that this is equal to 5 milliwatts is our output. All right, so 5 milliwatts is our output of our W dot or shaft work. What else do they give us? They give us, so I'm going to say for inlet conditions for a steam turbine, so I'll put T for turbine here. You could always assume, I'm going to say state 1. It's always safe to assume that this is superheated vapor, unless it's specifically stated that it's not. So because what's going on here is this turbine is connected to a boiler, right? And the boiler, what you want to do is, the goal here is to generate as much shaft work as you can with the energy that's being input through the boiler, right? So in order to do that, you need to get the steam as hot as you can handle it without breaking piping and doing that kind of thing. So usually it's very easy to achieve superheated vapor at the inlet. You want to achieve superheated vapor. So it's always safe to assume that, unless they tell you otherwise, right? Unless but they'll never, in this class for the chapter 5 and even in the exams, this will always be superheated vapor. So this is steam, so therefore steam means water, right? So we're talking the water tables in the back of the book. All right, so superheated vapor, we know that that's table A6. And what they give us, this is what it's given. So they give us the pressure at P, it's 2 megapascal. They give us the temperature at 1 is equal to 400 degrees C. And then they get kind of difficult on us. They give us velocity and they give us height. So the velocity of the steam is 50, and the height is 10 meters, right? So 50 meters per second. All right. So and then they give us conditions for state 2. Now we can't assume anything for state 2. We don't know if there's 3 possibilities. There's saturated liquid, there's saturated mixture, and then there's saturated vapor, and then there's superheated. It can be any of those 3 or 4. Again, it could be saturated liquid, saturated mixture, saturated vapor, and superheated vapor. It can be any of those. So for 2, we can't assume anything. We have to we got to solve it and let the clues tell us what it is. So let's take a look at this. For this problem, it's real simple what it is. I'm sorry, this is P2 now. It's 15 kilopascal. So T2 is equal to, so we have a drop in pressure, a drastic drop in pressure, and we have, we don't have T2. They don't give us temperature. Instead, they give us this quality. So the quality is equal to, the quality at state 2 is equal to 90%, right? So that's a giveaway what it is, right? And then they give us a velocity, 180 meters per second, and they give us a height of 6 meters. All right, so the giveaway of what this is this here. They give us quality, so therefore, by definition, whenever you have a quality, it's a saturated mixture. So it's the bell curve, it's in the center of the bell curve. So I don't think I did this for my other class, but no, I'm gonna refrain from drawing the temperature versus. Yeah, I'm not gonna draw that. But here's the giveaway. This is sometimes they'll tell you saturated liquid. Sometimes they'll tell you saturated vapor. This one they're telling us saturated mixture because they gave us a quality, and I should put a 2 here. And this is the velocity. And so the fact that they gave us velocity in, velocity out, height in, height out is indication that this isn't, we can't neglect, you can't neglect, what is it? Potential energy and kinetic. So this right here is the height difference, right? So right. So this is 6. It's 10 minus 6 is 4 meters, right? 4 meters is the height between here and here, because it's 10 minus 6, right? And the velocity, right? So you'll have to in your calculation you'll have to include kinetic and potential energy changes. All right, so so that's how you know this is superheated vapor. So I'm going to say we're trying to find, so in this one they were trying to find m dot, and then we're trying to find, let me look. It says determine, oh, so there's 3 things. Compare the magnitudes of, so they want us to find the magnitude changes of the enthalpy, of the kinetic energy, and of the potential energy. So those parts you have to calculate. And then finally they want to, this is part A, this is part B, and for part C, they want us to find the mass flow rate of this. No, well, I think I had that backwards. Determine the work done by. I'll just put it here. Work done by the unit mass. So they want us to find little w out in units of kilojoules per kilogram. All right. So all you need to know is that for this one, we know that the total work out is equal to the mass flow rate times the little work out. Right. So once you find the mass flow rate here, then you can find, and you know this is given here, work out. So then therefore you can solve for W for lowercase w out, right, in kilojoules per kilogram. Just keep that in mind. All right. So it's asking for m dot. So the way we do this, I'm just going to set this up. This is a steady state problem. All the problems in chapter 5 are steady state, at least the ones that I give, whether in homework or on an exam. So they're steady state, which means that simply stated, the energy that goes in is equal to the energy that goes into the system is equal to the energy that leaves the system. All right, so what does that mean exactly? All right, so we know that our system is the inside of the turbine. And anything that crosses this boundary that I'm drawing right now will be included in the energy balance equation. So there's 3 things for sure that cross it. Is there a heat loss, I think? I think there might be a heat loss. Let me check. Well, this is an adiabatic turbine, so there is no heat loss. So these are the 3 things. There's flow going in at state 1, there's flow leaving at state 2, and then there's work coming out here at the shaft, work dot out. All right, so now our equation is basically okay. So let's write our equation in its entirety. Let's see if this is the right place to put it. We don't have to write this equation out. Yeah, let's go ahead. So I should. So I'm looking at my notes. I'm getting. All right, here we go. So the equation is it's a long one. M dot times, so everything, so I'm doing E dot N. So it's M dot equals to H1 plus V1 squared divided by 2 plus G1Z, right? And then that's what's coming in, right? Nothing else here is coming in. The only thing coming in is what the flow coming in state 1, all right? Now we're going to say this is equal to everything that's coming out. Well, the first thing that's coming out is the shaft worked, and then plus m dot and H2 plus V2 squared divided by 2 plus GZ2. And that's it. That's everything, because we know that Q is equal to 0. It's Q, so there is no heat loss here, and we're not heating it up. So Q, if heat was coming out, it would have been on the it would have been here on this side too, on the coming out side. So this is the wonderful thing with chapter 5 and control volumes, is that we don't have to worry about that work shaft here is negative, right? Or is positive because it's coming out. We don't have to worry about that the flow coming in or coming out is positive or negative. All we have to do is stick to this equation here. Everything that comes on, we put on, that comes into the system, we put on the left. Everything that comes out of the system, put at the right. And we don't use any more sign convention. This is only for chapter 5. Chapter 4, a different story. right? But this is how you set this up. And then you, what you have to do is you have to, the only things that we don't know here, we don't know M dot. I'll put that here in orange. We don't know M dot, and we don't know our H's. But we do, we can get those H's, right? So the H, the way we get our H's is basically, I'll do that in blue, is to just look it up in the table, right? H1, let's look it up, A6, right? So let's go to our table. I think it's here. Let's go to A6. Okay, we know it's A6 because it's superheated vapor. And we know that because, well, I'll tell you why we know it for sure. But just a rule of thumb, it's always superheated vapor. But I'll show you another way to determine that. All right, so then we know that the, what was it? We know that the pressure is 2 megapascal and the temperature is 400 megapascal. So 2 megapascal, got to scroll down, is in red. Here it is. 2 megapascal, and then we're looking for a temperature of 400. So that means it's this row here. And we're looking for H, which means it's third, it's basically second from the right here. It's 3248, right? That should be our H. Let me make sure. 3248. Yeah, okay. All right, so we come back here and we say that this is 3248 kilojoules per kilogram. And now we found H1. H2 is not as straightforward. H2 is a little bit more drawn out. So we need to find H2. Well, H2, we know that this is, because of this is a saturated mixture. So we know the table here. We know we got to look up a table. We're given pressure, so we use a saturated water or saturated steam table, but the pressure one, which is A5. And we need to know, we can't calculate, we have to calculate H2. So if you guys remember, for a saturated mixture, we know that H2 is equal to HF plus X2 times HFG, right? So we have to calculate based on HF and HFG. So we got to go find HF2. And I mean, you don't have to put these down here, but since it's state 2, you could put 2 here if you want, and HFG2. So these are table values, HFG2, and this is equal, right? It's equal to HF at the 15 kilopascal pressure, right? And so if we go to that table, that's A5, 16, what was it? Oh, we're looking at H1, huh? H1 is, I'm sorry, H2, this is H2, sorry. So it's 15 kilopascal. So 15 kilopascals way up here, right here. And we're looking at, we're just highlight this whole thing here. All right, so we're looking at HF, it's 225.94. So again, that's 225.94 kilojoules per kilogram. And then HFG is, let's look at that table. HFG is given here, is 2372.3. That's kilojoules per kilogram. All right, so then we can calculate this right here, right? So I'm not going to calculate it here, but we know what X2 is, right? It's 90%. We just found HF and HFG. So it turns out H is equal to H2. And when you do the calculation, is I don't think that's necessary to write it out. Yeah, I'll let you guys calculate it out. So this is how you set up the problem, and then it gets a little bit more complicated, right? Because now you have. Let's go back to this equation. This is what's going to give you your m dot, right? You have the green light here because we're almost done. Now you have your H1 and your H2, right? H1 we got from the table. H2 we calculated. You have your V's and you have your G's. You have your workout. Now you just solve for m dot, right? You just solve for m dot, and that gives you a. Now your B here and your for this, you basically just have to look at delta H, delta K E, and delta PE. Delta H basically it's H2 minus H1, or actually you always look at the hottest energy, right? The hottest energy is incoming, right? So your delta H is going to be H1 minus H2, because this has the highest energy here, and this has the lower energy, because what happens, we're pulling work out of the workflow, and then it comes out this way. So to delta H is that, right? And delta KE is the kinetic energy, is basically V. It's, what is it? It is V2 squared minus V1 squared divided by 2. And why? Well, it's because the higher velocity is at state 2, or the where it comes out. And so, if we did it backwards, it would be negative, right? We're trying to compare. We're not getting negative kinetic energy. I mean, we're getting a drop in. Okay, let me back up a little bit. We're just comparing. We're actually comparing. Hold on a second. The enthalpy energy. I can't erase this. Versus the kinetic energy versus, or the enthalpy change versus the kinetic energy change, and versus the height, the potential energy change. So actually, because we're doing that, we should just keep our indices the same. So we should just have this as 2 and 1, and therefore potential energy is equal to what is it? It's equal to G times Z2 minus Z1. All right, so then you compare your energies, and you're going to find out that for sure the potential energy change is negligible, because it's only, your flow is starting at 4 mil, it's changing 4 meters in height. It's not, it's not changing. It's not like a waterfall of high flow rate water is coming down a 40, for like those hydroelectric power plants problems that we were doing. It's, it's just only 4 meters, and this is steam, it's, so this is really negligible. Kinetic energy isn't as negligible, but it's small. The change in enthalpy is the largest change that you're going to see. So this work out here is almost entirely due to the change in enthalpy. And the change in enthalpy is basically your flow, right? It's your energy due to the flow that comes in and out. It has nothing to do with the kinetic energy. It has more to do with the pressure and the temperature than anything else. All right, that's all I wanted for. So follow the video right in our Beachboard media gallery for the rest of this problem. I want to start on chapter 6 now. All right, so introduction to chapter 6. Let me just start a new page here. All right, so this is the second law of thermodynamics. All right, so for the second law of thermodynamics, so we're talking the second law. And the second law gives us, what it does, it gives us direction. And that means like whether it's heat flow or just energy flow in general. Like we all know that heat travels from hot to cold, right? We know that this Q travels from hot to cold. But does anyone know why? So it doesn't normally, could Q, so, or spontaneously, could Q go this way from hot to cold? And now, it could, but statistically, in other words, it is possible. I mean, it is, you know, I mean, physically it is possible, but we're talking spontaneously. So we're not talking forced, right? Forced, yes, I can, an air conditioner does this. A refrigerator does this, right? A refrigerator gets heat out of our cold box, you know, which is attached to here, and dumps it to our, you know, radiator at the bottom of the refrigerator. So it could be done, but you have to add energy. You have to, this requires work. So it can't happen spontaneously. This one happens, yes, spontaneously. It doesn't require any work. It just happens, right? But can you explain, anyone explain why heat always travels from hot to cold? The explanation lies in the second law, but really what it does is energy flows from a high energy state to low energy state, right? And so the short answer is that's why heat travels from hot to cold, because we know that anything that's hot has a lot of energy in it, and it's dense energy, right? So it's that's why it's hot. So there's a lot of molecules moving around, for example, in a hot solid, right? So that's why energy, you know, the energy will spontaneously flow from a high energy standpoint to a low energy standpoint. So that's not covered in the first law. All right, the second law gives you that. So another example of direction. Let's suppose, why did I do that? Shoot. All right, here we go. All right, let's suppose we have a mug. All right. Okay, I don't know why I can't do black here, but whatever. Let's have coffee here. All right, we can do a blue cup of coffee. All right, and then let's go, you know, this is our coffee here. And now we start off with, let's just suppose we start off. Anyway, we start off with 10 kilojoules, right? And now we're going to have, and let's say the temperature of the coffee is, I don't know why I can't change colors. I don't know what the heck's going on here. But let's say the temperature is equal to 50 degrees C. But then we're going to have, what's going to happen is we're going to have heat. Oh, there we go. Heat is traveling that way. we're going to say the heat loss is equal to 2 kilojoules. So then what's going to happen is sometime in the future, what's going to happen is that we're going to have 10 kilo. So 10 minus 2 is 8 kilojoules. And we'll probably have a temperature drop as well too. The temperature will probably be something like 35 or something. And we're just, the assumption is the outside is colder than the coffee, right? So the ambient is equal to, just say it's 20 degrees C. So this is covered by the first law. So all the first law tells us is that we had some energy loss, and now the energy went from 10 kilojoules to 8 kilojoules, and we had a drop in temperature, and that's it. And then so that we satisfy the first law of thermodynamics. The first law doesn't tell us, well, what if it happens the other way around? What if we have heat coming in and it's 20 degrees C and the coffee is 50 degrees C, it's hotter, and it's still 2 kilojoules. And now we went from 10 kilojoules to, we added, so we have 12 kilojoules, right? Instead of the 8 kilojoules, because we just gained some from this 2 kilojoules. And therefore the temperature started at 50, now it's 50. Let's say now it's equal to 55. It was 50. All right. That doesn't make any sense, right? We can't have energy just, it's colder outside than the coffee is. So how can energy just go in spontaneously? It can't, right? We can force it in. Sure. I mean, we can, but it's not going to be at, it's going to violate. We're not adding work. The only way we can force it in is through work. So but lo and behold, the first law it's still okay. This will still be okay with the first law. This is okay. The fact that energy can go from cold to hot is okay. The first law doesn't have anything to do with that. You just have to account for the energy. So if I said instead of having 10 kilojoules now, I gain 2 kilojoules, and now I have 12 kilojoules, I'm okay. The first law is okay. You can go to a patent attorney and say, I have a machine, or I have a coffee cup that absorbs energy from it's a hot coffee, and it can absorb heat from the outside and not only will it keep the coffee from getting cold, it'll warm it up, right? And if the patent attorney said, well, okay, but if I told them you only can use the first law of thermodynamics, they'll say, oh, you pass. This passes the first laws of thermodynamics. Now it's the second law that it doesn't pass. All right, it does not pass the second law of thermodynamics. All right, does not. Because the second law tells us that heat travels from hot to cold. And that's just kind of a, how should I say it? I'm just telling you, I'm not giving you an equation of why that is. I'll do that next time, or actually on chapter 7. All right, the other thing is, okay, sorry, just turned off my air conditioner because I'm in a sealed room here. Speaking of energy, right? If you have a computer on, I have me in here, the room heats up, so got to cool it down with energy. All right, so the other thing I wanted to mention is speaking on the topic of directionality. So the second law gives us, I don't know if this is the right word, but I just call it directionality. Or this is, I'm just messing around here, one wayality, which is stupid, I know, but maybe I should put that in parentheses. All right, so that's what the first law gives us. All right. The second law. So this is the second law of this here. Wow, it's all loud all of a sudden because I turned off my machine. I can. So second law. All right. So another example would be you have a vessel and you have water. Okay, I don't want to do this again. Right. You have some water in here, and then you put a propeller in here that you can spin, right? And by doing so, if you spin this propeller, you create heat, right? So what happens is heat will start, this water will start to, it will start to get hot, and what's going to happen is you'll have heat coming out. So Q. So can we do this in reverse? If we didn't have the second law, can we do this? See, what would be the opposite of this? Okay, the opposite of this would be, you just set up the problem. Just try it over here. So propeller, the opposite would be, what if we put heat in? So the reverse of this is we put heat in. Are we going to get work out? Right, so we put work in, do that right here. We put work in, right? And so the work in causes heat to come, heat dot to come out. Now we put heat dot in. Will we get work? Or are we going to get anything coming out like that? And that's the question. And then the answer is no, right? Just because we heat up this glass of water, this propeller doesn't start to spin, right? Because it's not. You inside here you have molecules that are, moving randomly from one side to the other. They're just, you get random bouncing around, but that just basically doesn't. You don't have any directional bouncing, so therefore you don't get any energy coming out by doing a reverse. So therefore this violates the law of the second law of thermodynamics, because it should be one directional, right? Because in these situations, this is more an easier way of looking at it. Suppose you have a resistor and you put a potential across here. Well, that potential basically creates a current that goes through the resistor, and the resistor heats up. So you get Q coming out. Now let me do the reverse. Well, the reverse works. So the reverse is, I put heat in to the resistor. Can I generate, will that heat in cause current to flow? And then therefore to create a potential? And the answer is no. So no, that won't happen. And that's because of the second law. You can't, the nice thing with having intuition is that we know that if we heat up a resistor, that's not going to happen. I'm talking about a normal resistor here. I'm not talking about a thermoelectric heater, which is it's really a heat engine. You heat one end, you cool the other, and then you can produce electricity. So by just heating the resistor, the resistive element, this will not happen, right? You're not going to get that, and you're not going to get that, and you're not going to get it. Therefore, you're not going to get current flowing. Okay, all right. So that is the second law of thermodynamics in a nutshell. That takes us through these and this one. All right. Now I need to talk a little bit about, this is where I left off at the next. So next meeting, we're going to be talking about heat engines. And these are engines basically that use, just like the previous example showed. Let's see. Oh, the next one. Sorry. A heat engine basically uses heat from a source and it throws some heat away into a low so it takes heat or energy from a high temperature source and it converts it to work, but we have to also throw energy into a low temperature source. So maybe what's the best way of wording it? Taking energy from a high temperature source, throwing some waste heat into a low temperature source, and then producing energy or producing work. That's what a heat engine does. This is necessary here. Okay, we have to throw away, Q out. In order for this to work, the second law of thermodynamics, and I'll explain either today or next week, is that a heat engine must throw away some of its energy into a low temperature source. So your car is a heat engine. A steam power plant is a heat engine. A refrigerator is a heat engine in reverse. And so is an air conditioner is a heat engine in reverse. We put work in and we get, we produce a low temperature sink, and we throw away heat into a high temperature sink source. Lots of types of heat engines. A thermoelectric generator is a heat engine. What else? There's different types of engines. There's a diesel. We'll talk about in chapter 9. There's just the normal gas or gasoline engine, what we call the Otto cycle engine. Then there's jet engines, and there's just different types of engines, but there are different types of heat engines. But they all work on the same premise: getting energy from a high temperature source, throwing away some energy into a low temperature source, generating energy or work. Okay, and when we mean by source, we mean we use these words called reservoir, and it's just a hypothetical body of water, or it can be anything else, where we have thermal energy capacity. So it basically means that it doesn't tend to want to change temperature. And for example, if we had a power plant that was next to the ocean and we were dumping our heat into the ocean, well, we don't expect the temperature of the ocean to rise. Now, locally it might, but we're showing even locally it's not going to rise that much because it's such a large body of water that even if you put megawatts of energy of heat into the ocean, it's not gonna change the temperature of the ocean, or a large lake, or even a river, because it has flowing water. So these are considered thermal sources, energy sources, or sinks. So a source would be where we're grabbing the heat, the energy from. These, what I show you here, the atmosphere, river, lake, and ocean, they're all sinks. We don't grab energy from these. We don't do cryogenic type of energy conversion. So these are just sinks. We just grab, we get our heat sources from something like a boiler or a gas engine, and those are the thermal energy sources. But those are your sinks here, usually your cold sinks. Right. And then the famous the most famous, well, at least in this class, the heat engine is basically our steam power plant. So see how much time we have. Steam power plant, I'll just lay it out real quick. You start off with, okay, sorry. I'm gonna try to stay clean here. So I'm gonna start off with a box like this. And then I'm gonna say, this is my boiler and my condenser. So I'll start labeling it. This is my condenser. Here's my pump. take that back. That's not my, how can that be my condenser? I got a turbine here. So for this one, I need to draw it. Then I have my condenser. And then I have a pump. So this is my boiler. Over here is my turbine. This is my condenser. And here's my pump. All right. All right, so the purpose is basically to have the turbine spin so we can get some work out. But for that to happen, we have the boiler needs to put energy into the stream. So we do have so what we say, we usually do it this way. We almost label it like some outside source is going to put heat into this boiler. So this outside source can be just it could be internal to the boiler, but this is the way we put it. It could be the gas flames that heat up the water, right? And then you're going to have you know, steam is going to be flowing this way, right? And it's going to then so this is steam, superheated vapor steam. And then it goes into your turbine. And when it comes out of the turbine, it comes out as, usually it's saturated. I shouldn't say that because I don't know for sure. But it just comes out as some kind of a, it comes out as some kind of a mixture, or it could even be superheated vapor. It doesn't really matter. But then it comes this way, and then it goes through a condenser. Now the condenser has water cooling usually, or air cooling coils. And so what it's going to do, it's going to be able to reject or take water or take heat out, right? So it removes heat out, and now you have at the bottom of the condenser, you have water collects, right? And you got water collection because it's condensing. This is steam, right? So then now you have water that you pump, that gets pumped back to the boiler through the pump. So you got water going this way, goes through the pump, comes out this way, right? Now the pump is, right, we have to put work in to get the pump to run, right? Now the work in is very little compared to the workout. So usually workout is way larger than work in. So to the point where almost work in is negligible. So the work in is basically just to grab this water and pump it back to the boiler, and therefore, you know, completing the cycle, right? So that's our, you know, what do we call this? A steam turbine. This is what does the book call it? Steam power plant. Okay, so this is your steam power plant. I think I captured everything. Now, yeah, this is your steam power plant. Now, one thing, well, I'll talk about this next time, but this is necessary, all right? You can't complete the cycle without condensing and pump, because even if I told you a pump only pumps liquid, it can't pump vapor, right? This is still necessary. We have to throw away energy. You have to throw it away. So therefore, the work that comes out of the turbine is never 100%. Never could be, not even 90% efficient, because this energy, usually for the temperatures that we operate in, you know, this efficiency of the turbine is usually no greater than 40%, right? So you can never, the second law of thermodynamics tells us that you can never get anything better than about a 40% efficient turbine. Maybe 50 if you're like, if you've found, you know, maglev bearings or something. or did something weird. But you'll never. We have to throw energy away. It's just the law of the. It's the second law of thermodynamics. Therefore, as we industrialize, as we get more and more people, and we put more energy, we have to throw it. Your car has a radiator, and it's there because of the second law. And that energy will keep warming up the environment, and there's nothing we can do. We can make things as efficient as we can, but there's still energy that has to be thrown away. And that's the second law. We can't defeat it, and we'll talk more about it next meeting. Okay, on that last gloomy thought, any questions? We'll leave it up right now for some questions. Then if no questions come in for this, we'll go into our office hour part. So you guys have any questions, let me know. If not, then you guys are, have a good next couple of days, and we'll see you on Thursday.
Thank you, Professor.
Okay, you're welcome, Marco.
Thank you, Professor.
You're welcome.
Have a good night, Professor.
All right, guys. Now I'm losing my voice.
Hi, Professor.
Mm-hmm.
I have a question. I just saw something that Rocket Lab, it has a launch tomorrow. Do you know what time, and do you know anything about that?
Yes, I do. It's going to launch at 1400 hours. So it's actually like 14. So it's like 2 Pacific Standard Time. Somewhere around between 2 and 2:30 is the first launch opportunity. Yeah. So it's going to launch from New Zealand. So I'm not there. My coworker is. I have a coworker we're running some thermal testing, and he had to go, and so he's going to get to see it. But yeah, thanks for bringing that up. It's going to start on the 21st, so it's tomorrow, 2:00. Yeah, so they say that the weather is a little weird. Right now in New Zealand, they're kind of coming out of winter, and so it might rain if they won't. I think they'll launch with a little bit of rain. Don't quote me on that, but one of the biggest worries is high wind, like high wind shear and all that. They won't launch if there's a lot of wind, so it's kind of in the middle. They may or may not, depending on the weather tomorrow.
And did they pick New Zealand for a specific reason, or like their website says that they have 2 launch sites that they can launch from, like California, or they can launch from New Zealand. Does that depend on the orbit that they're trying to get to with the specific satellites?
Yeah, good point. It does. It helps to be closer to the poles, right? If you want a polar orbit or what we call a sun synchronous orbit, which is kind of like a polar orbit. It's almost like the satellite going around the poles, but not quite. The sun synchronous just means that your spacecraft will always be seeing the sun, no matter what. And those are pretty stable orbits, and yeah, it's easier to get there from New Zealand. But actually, the real reason, and the CEO is Peter Beck, and then I didn't know this until I saw he told us, but I forgot, and I saw his TED. He gave a TED talk, and it's because New Zealand. Well, he's from New Zealand for one, but it turns out, airspace is a big deal, right? So every time SpaceX or NASA launches a rocket, because they're the only people that launch from the U.S., right? SpaceX, NASA, or UST or ULA. Not too many companies launch, right? There's a few out there, but ULA, SpaceX. What happens is airspace is a problem if you launch from the U.S. because we have so much jetliners, right? Air traffic, that what happens is when they launch a rocket, you have to stop airports, right? You basically any flights going into the East Coast will be stopped until that launch happens. And that's one of the reasons you'll see flight delays. You'll see lots of flight delays on days when there's launches. They don't have to worry about that. No one goes to New Zealand, right? I mean, it's a nice place to go to. I'd love to go there, right? And they film Lord of the Rings there, right? I want to go. I want to check it out. But no one goes there, so they have plenty of launch opportunities. They don't mess with the airspace, and so it's much cheaper to launch. They can launch every other day and not cause any problems. Where At the U.S., there's no way you get to launch once a month if you're lucky. SpaceX got I think they get 26 launches a year, and that's it. So that's the reason they're in New Zealand. And they have one. The second launch facility is not in California, though they may put one in. It's actually in Wallops, Virginia, and that was only because we're starting to fly now. I say they because technically I'm still a NASA employee until January, but we're starting to fly government rockets. Things like for NASA, and so therefore by law we're not allowed to launch government property from anywhere besides the U.S. And so that's why Rocket Lab now has a launch site from the U.S. But that's the only reason. We could launch from New Zealand and get a better, like a more of a. It doesn't have to be. It could be one of the beta orbits. The lower beta orbits, anywhere from usually no less than 30 degrees or something. But the real reason is because of politics. It has to be, if we want to launch a U.S. rocket, it has to come. Even though Rocket Lab is a U.S. company, we can't launch U.S. government satellites from New Zealand. Yeah. Yeah. Thanks for bringing that up, though. That's got me a chance to talk about my company.
And then there's NASA's. I don't know the name of it, but they launched a satellite thing that a few years ago. That today it reached the asteroid Bennu.
That's right, Osiris
Yeah.
X. Yeah.